calculations involving chemical reaction engineering process has been made by means of mass and enthalpy balance. It's known that in a well-mixed system, the work aided by the steering system is usually neglected. Such consideration can interfere directly in analytical procedures for non-reactive and reactive systems. In its work, the methodology of analysis and optimization is known as Entropy Generation Minimization. Such methodology is based on the classical principles of thermodynamics, heat transfer, and fluid mechanics. Notable contributions on minimum entropy generation have been made by the following authors: Bejan, Johannessen, Anderson, Mansi, Bisby, and Thomas. However, why use the entropy? Using entropy together with other thermodynamic functions is an alternative and convenient form to establish optimal operating conditions. Once the minimum entropy generation rate is determined, the optimal global operating points can be reached in reactive or non-reactive systems. In addition, such studies can be applied in the development of advanced control strategies. Some publications of our research group can be observed in the last years, starting with analysis and optimization of a CSTR by direct entropy minimization, published in Journal of Chemical Engineering of Japan in 2008. In its work, a CSTR reactor has been analyzed. In its context, a first order, irreversible, and exothermic reaction occurs. The analysis results in an equation to describe the entropy generation rate for this reactive system. Then, using classical considerations for optimization, the relationship between the inlet and the reaction temperatures can be obtained, allowing the optimal reaction temperature determination where a minimal entropy generation rate is observed. The second work is entitled Direct Entropy Minimization, applied to the production of propylene glycol, published in Chemical Engineering Process in 2009. In its work, the result of analysis showed that not only the temperature have influence in the entropy generation minimization, but also other variables such as the residence time. Once more, using classical considerations for optimization, the new optimal global operating points can be determined, resulting in an improvement in the reaction conversion. Therefore, for conversion rate in the reactive system, it's necessary the increase of the reactor residence time. So, keeping the same feed flow rate, it's necessary to change the structure of the reactor. That will probably affect the overall process, resulting in economic consequences. In 2011-2013, with the aim of an explanation of the molecule's behavior, the classical Maxwell-Boltzmann equation has been used, showing a more uniform distribution in the molecule's velocities when the reactive system is optimized by HM method. In 2012, the application of this methodology in advanced control has been made, resulting in a better response time when compared with the classical proportional integral controller. One second. Sorry, one second. In 2013, the analysis of the crystallization process of the monochloroacetic acid has been made, where the entropy generation rate for the crystallization process has been obtained. The main objective of this work is analysis of mechanical work transfer in transfer to the process apply to the following cases, in which the non-reactive and reactive systems are operated in stirred tanks. The first study deals with the crystallization process of the monochloroacetic acid. This crystallization process was developed by Gomes in 2012 and can be described by means of the following equations for mass balance. Since the classical methodology for enthalpy balance can be given by this equation, in this work we have considered the mechanical work transferred to the process through the power consumption, where P represents the energy transferred to the process by the impeller and can be given by this equation. P can be obtained by dimensional analysis based on Halef and Buckingham methods, taking into consideration all dimensional variables applied to steel and tanks. After some considerations, the enthalpy balance for the crystallization process can be given by this equation, taking into account the mechanical work transferred to the process. At the same way, the entropy balance can be given by this equation, where this term represents the entropy generation rate. After some consideration, it's easy to show that the entropy generation rate for the crystallization process can be given by this equation, taking into account the mechanical work transferred to the process. The second case deals with the production of propylene glycol by hydrolysis of propylene oxide. This reactive system can be described by means of the following equations, which represents the mass balance and the enthalpy balance, taking into account the mechanical work transferred to the process. The entropy balance for this reactive system was developed by Mans et al. In 2009, thus taking into account the mechanical work. The entropy generation rate for this reactive system can be given by this equation. So, the analysis of the results obtained through analysis of the mechanical work transferred to the process can be observed as follows. For non-reactive system, the analysis of the figure 2 enables the influence of the impeller to be observed in the crystallization process of the monochloroacetic acid, in which the increase in the speed rotating results in an increase in the entropy production rate in spite of the temperature of the system. If we compare the crystallization process without stirred system given by this equation and shown in the figure 3, with the crystallization process given by this equation and shown in the figure 4, it can be observed an increase in the entropy production rate when the mechanical work is transferred to the process, in agreement with the theoretical prediction of thermodynamic behavior. Such behavior can yield a significant impact on the design of the cooler systems. The analysis of the reactive system has made it possible to verify the influence of the work transferred by the impeller, as well as the increase in the conversion as compared to the system proposed originated by the literature. So, the figure 5 shows the conversion rate for the reactive system, where the headline represents the conversion of the system originally proposed when the mechanical work is not performed by the impeller is not considered. The blue line represents the optimized system by AGM method, resulting in a maximum conversion for a particular residence time in the reactor. However, the results obtained by AGM can reproduce when the mechanical work transferred to the process is taken into account. To it, this also yields a maximum conversion, keeping the original reactor residence time, as can be observed in the green line. The figure 6 shows that the entropy generation rate for this rotating, where the head point represents the minimal entropy generation rate required for that the process operated. When I specify impelled rotation is used joint with the reactor, original reactor residence time. The Maxwell-Boltzmann analysis has been made with the aim of to explain the influence of the impelled diameter in the conversion rate. Therefore, for particles probability distribution for the several impelled diameter has been obtained. It can be observed that when the impelled diameter is increased, the reactive is increased, a greater amount of particle, a better energy distribution can be obtained, resulting in a maximum conversion for the reactive system, keeping the original reactor residence time. In conclusions, the work transferred by the impeller to the book was obtained by means of dimensional analysis, and its introduction to balance equations enabled the degree of freedom of the system to be increased. In accordance with the results obtained, the introduction of energy into the system in form of work done by the steerer should be considered whenever possible. Such a fact is important at the least for optimization procedures, or otherwise, such procedures can lead the system to producing suboptimal solutions. It's important to mention the low computational effort and the lower cost of implementing and operating such methodology, which emphasizes that its potential for use in industrial applications is promising. Some reference. I would like to thank the Federal University of Campina Grande, the CAPS, and the Federal Institute of Paraíba by financial support, and thank you for your attention.
Thank you very much. Is there any question? You show me a figure about the interference and different curves. The ratio of the diameters is belong to the is ratio of the curves. You put different diameters.
Yes.
And what is the ratio of the diameters and what is the ratio of the
Yes.
curves?
Yes. A great energy distribution has been obtained when the impelled diameter is increased. The particles has been the same energy cinetic, and they result in a better conversion rate in the system.
Any questions?
I have a question. Gaetano Portugillo, Universidad del Sannio, Benevento, Italy. You showed a figure in which you demonstrate a 0.4 conversion without taking into account the before.
Yes.
And much higher conversion when you take into account the mechanical work. It is a very big difference, almost unbelievable. How do you explain this physically? Yes, you have a below 0.4 conversion.
Yes.
If you do not consider mechanical work. What is the explanation?
In the first case, the optimized system by aging method.
This is a typical result from Fogler. That is a very useful exercise in the text or in the textbook, and the reference is the exercise from Fogler, and the line that is normally result for the industry. This is the conversion rate for this. The another, when you use the social methodology, and we can reach the better conversion rate for this system. That is, normally we have at the moment used only the first law of thermodynamics. When you use first with the second law, we receive a better result for the system. It is clear. It's clear.